All right, so we had started the lecture on this chapter 11, magnetic fields. I'm going to briefly review it, then finish this lecture and maybe do some problems from it, okay? So we were talking about magnetic fields. We learned that, okay, so these are the Maxwell's equations. Yeah. Classically, they describe all of electromagnetic phenomenon, all of electrical engineering. The basis of that is essentially in these four equations. Okay. What we saw was charges create electric fields. Okay. And moving charges create magnetic fields, and the magnetic field configuration is so here it is. So if the charge is moving along the axis of the cylinder, okay, so magnetic fields are tangent to the cylinder. Okay. So you saw that charges create electric fields, moving charges create electric and magnetic fields, but here is the configuration of the magnetic field. Okay. And that's what this equation is telling you. So you saw that the cause was on the right-hand side for these equations, and the effect was on the left-hand side. So we are only talking about this part of the equation. This is current density. When do you get currents? You get currents when you have charges moving, and these charges are creating this magnetic field. Yep. Time-varying electric fields also can create magnetic fields, but we'll talk about that in a later chapter. Okay. So in this chapter, well, in this and next chapter, we'll talk about moving charges creating magnetic fields. Okay. So the form of this equation, for instance, will tell you this thing, and we saw this. Okay, so if you had an infinitely long current, straight current, it would produce magnetic fields that are like that, tangent to concentric circles. Okay, so that's what this equation is telling you. Okay, so this current produces that magnetic field. Okay, you'll also learn that a current like this, okay, a circular current will produce magnetic fields like that. Okay. And this is very good because if you went into a store and bought a magnet, okay, the magnetic field looks just like that. Okay. But this is very neat. Why is this neat? This is called an electromagnet. Okay, so here you went and paid good money and bought this magnet. Let's say you got tired of the magnetic field and you want to turn it off. You can't do that. This thing, just switch off the current. And that is very useful. You can turn on the magnetic field whenever you want and turn it off when you don't want it. Okay, so this is an electromagnet. Okay, a current carrying loop is an electromagnet. Okay, and again, you guys are experts at circuits and all. So there is a switch. Okay, there is the wire. You pass the current through this. Okay, so the way I guess. So close the switch when you want the current, when you want the magnet, and when you don't want the magnet, just open the switch. Did you guys understand that? Okay. All right. These equations are the same laws written in integral form. These are the same laws written in differential equation form. All right. So what does this equation say? Okay, again, charges produce electric field, moving charges produce magnetic fields. Okay. So we've said this before. They produce electric fields, and to detect the electric field, you need a charge. So there is the beautiful symmetry. Okay. Moving charges produce magnetic fields, And to detect this magnetic field, you need a moving charge. Okay? So this magnetic field, for instance, cannot be detected by a stationary charge. The charge has to be moving. Okay? All right, and that's what this equation is telling you. This is the force. If you have an electric field, how do you detect it? You put a charge there and it'll feel a force. Okay? If you have a magnetic field, how do you detect it? You throw a charge, okay, a charged particle, and that'll feel a force, and that's the force. You guys understanding this? Okay. So for instance, if you had a neutral charge, if you had a neutral particle, you couldn't detect a magnetic field. Okay, you can do anything you want with the neutral particle, but you can't detect the magnetic field or the electric field. Okay. All right, so here are various shapes of magnets. Now we'll talk about how we learned about magnetism, the history of it. Okay. So this is how you encounter magnetism. So you have magnetic materials which have north and south poles. Like poles repel each other. So north pole will repel a north pole, south pole will repel a south pole. And unlike poles attract each other. Okay? But now eventually you learn that if something is magnetic, that means there is an unbalanced current in there. So there's a moving charge that is producing a magnetic field. Okay? All right, so again, if you break a magnet, you get two magnets and so on till you get to the atomic level, essentially. Okay? So here's a bar magnet. Okay? Again, we saw all of this. And what it does is it creates a magnetic field all around it, all the way to infinity. Okay? And that's assuming this magnet was put there a while ago. Okay? All right, how do we detect this magnetic field? Well, you need a moving charge, but you can also use other magnets to detect the magnetic field. All right, so if you place a magnet here, a little compass is essentially a magnet, and this compass will line up with the magnetic field. Okay. Well, what is happening is the North Pole is being attracted by the South Pole, and the South Pole is attracted by the North Pole. Okay. And so this magnet will line up tangential to the field lines. Okay. So that's what you're seeing here. All right, this is one of the most important equations that you need to know as far as solving problems go. Okay, what is this equation telling you? The force on a particle due to the magnetic field. Okay. And again, to detect a magnetic field, what do you need? You need a moving charge. If Q was 0, the force would be 0. If V was 0, the force would be 0. Okay? So you could have a charged particle, but if it was at rest, the force would be 0. Okay? So, the force on a moving charged particle is Q times V cross B. Okay? So let's say if the particle was moving in this direction, and there's B, the force is perpendicular to the plane containing V and B. Okay? And the way to figure this out is, if you let's say you turn a screw in this direction, if you turn a screw in this direction, the screw would move up in that direction, and that's the direction of the force. Okay? So you turn from the velocity vector to the magnetic field vector, and the direction of the force would be the direction in which the screw moves would be the direction of the force on a positive charged particle. If it was a negative charged particle that was moving in this direction, you just figure out as if it was a positive charge, and if it was a negative charge, the force is in the opposite direction. Okay? All right, so again, the magnetic force on a moving charged particle is this cross product. The magnitude of this force is QVB sine theta, where theta is the angle between the two. And you know that sine 0 is 0, sine 180 degrees 0. So if the particle is moving anti-parallel to the magnetic field, it will not feel any force. If it is moving parallel to the magnetic field, it doesn't feel any force. So those are the only two directions when it doesn't feel a force. In all other directions, it'll feel a force. Okay. All right, so again, very important relationship. You want to make sure you understand it. Okay, so here's the right-hand rule. You point your thumb in the direction of the velocity. This is for a positive charge. There's the direction of the magnetic field. And again, if you turn a screw in this direction, the screw would move out. Okay, that's the direction of the force. Okay, again. So here's the force on a charge in the presence of an electric field. Here's the force on a charge, moving charge in the presence of a magnetic field. Okay, the force on a charge in an electric field is in the same direction as an electric field. Okay, and so an electric field can speed up a charge or slow down a charge. This force is perpendicular to the direction of motion. Okay? And when you apply a force that's perpendicular to the direction, you cannot change the speed of a particle. All you can do is deflect it, make it go in a circular path. Okay? So magnetic forces cannot do any work on a charged particle. And you cannot increase or decrease the energy of the particle. Okay? Okay, this slide tells you what the units for the magnetic field are. So if you wanted to find the units of this guy, all you do is take force, divide that by that. So force divided by charge times velocity. So to figure out the units for this are newtons. The units for charge are coulombs. The units for velocity are meters per second. Okay. And so you can write this combination of units in another way. Coulombs per second is an ampere, so Newton ampere per meter. Or also this combination of units is called a Tesla, after Mr. Nikolai Tesla, I guess supposedly one of the greatest inventors, at least in the 18th and 19th century. Okay, so the SI unit for magnetic field is a Tesla. Now, planetary magnetic fields happen to be about 10,000th of a Tesla, and so we have a new we use a unit called the Gauss to measure, let's say, the magnetic field of the Earth. Okay. The magnetic field of the Earth is about half a Gauss. Okay. So this is where we stopped last time. Okay, so now FSU has a National High Magnetic Field Lab, and they can create fields about 100 Tesla. Strong MRI machines can create. MRI machines use magnetic fields from 1 to half to 3 Tesla. Okay. The stronger the field, the more expensive the image, and the sharper the image. Okay? So if you want better resolutions, you want a stronger field, and it costs more. Okay. So if a doctor wants to see a tiny tear, then you want a better resolution image. If it's a big tear, then a small resolution image is good enough, right? Okay. So when neurons in your brains fire, there's charges moving, they create magnetic fields, and that is the strength of the magnetic field, a trillionth of a Tesla. Okay. All All right, so this shows you the magnetic field of the Earth. Okay, so there's half a Gauss, I mean 0.3 Gauss. There it's 0.6 Gauss, okay, near the field, near the poles. So again, so here is the North Pole, here is the South Pole, and the Earth's magnetic field is like that. It's as if the North Pole of a magnet was buried there. Okay. That's why if you take a compass needle, the compass needle will point that way. Okay. The compass needle will line up like that, and it'll point to the north. All right. We will need to, so in this chapter, you'll need to do problems where you have to visualize things in 3 dimensions. Okay. So you will need to indicate the direction of a magnetic field. Okay, and the device used is, think of an arrow. Okay. So the magnetic field is pointing along in the direction of the arrow. If you're looking at it like that, so if the magnetic field is pointing at you, what you're seeing is the arrowhead. And so there is the tip of the arrow. So dots represent magnetic fields coming out of the plane of the paper. Okay. And if you're looking at the magnetic field like that, okay, so you're looking at the tail of the arrow, so the crosses indicate magnetic fields going into the sheet of paper. Okay. And of course, so this is magnetic field coming out of the paper, this is magnetic field going into the paper, and if the magnetic field is in the plane of the paper, that's easy to indicate. Okay. Okay, now what this shows you is the following. So here's a magnet, and here's a wire that is passing between the poles of the magnet. Okay, now so this is showing you that. So you see the magnetic field is pointing like that, and so in this perspective, the magnetic field is into the plane of the paper. And right now there is no current in the wire. When there's no current in the wire, so in a metal wire there's free charges, but when there's no current, those charges are not moving. And so there is no force on those charges. Remember, when charges are not moving, there's no force on them. Soon as you pass a current, okay, so now in a metal, the current is actually due to negative charges flowing in this direction, but let's say, for argument, we'll say these are positive charges moving like that. So whenever you have a charge moving in the presence of a magnetic field, then it'll feel a force. Okay, let's figure out the direction of the force. Okay, so in that wire, you had a positive charge that was moving in this direction. There was the velocity. The force is V cross B. V cross B. B is into the plane of the paper. So V cross B, if you turn a screw that way, the force will be to the left. Yeah. So when you have a wire carrying a current, there's a whole bunch of charges moving. Each charge feels a force in that direction, and so the wire feels that force. Okay? And the wire is deflected in that direction. If you reverse the current, the force will be in that direction. Okay? How long do the charges feel the force? Only as long as they're in the magnetic field. Soon as the charges come out of the magnetic field, they don't feel the force anymore. You guys understand that? Okay. So they feel the force only as long as they're there. Okay, so the force on this current carrying conductor that's the force on each charge. And that tells you how many charges there are in that wire. Okay, N is the density of free charge density, A is the area of cross section of the wire, and L is the length of the wire that is in the magnetic field. Okay, and these guys combine to give you Q times V. V is the drift velocity times N times A gives you the current in the wire. So the force on a current carrying conductor is I L cross B. L is a vector in the same direction of the current. L is the length of the wire in the direction of the current. Okay, and this length is the length that is in the presence of the magnetic field. Okay, so since a current is a bunch of charges moving and each charge feels a force, a current carrying conductor feels a force, and that's the equation for it. And notice, if the current is zero, the force is zero. Okay, larger the length in the magnetic field, greater the force. Okay, okay, again, you would use the right hand rule for that. So for this problem, there is L. Okay, that is L, if that's the direction of the current. Okay, so right now the current is zero, but all right, so let me draw it here. So for this guy, there is L, that's the L vector. For this guy, this is L vector. Okay, all right, so there's the force on it. Okay, a current carrying conductor feels a force in a magnetic field. Okay. All right, so what we are doing here is now so we initially started with a straight wire, and we saw that it feels a force. Okay. Now the next thing to do is the next logical progression is, what if the wire is not straight? What do you do if the wire is not straight? You learned calculus, break it up into little pieces, and each little piece is straight. And you know how to calculate the force on each little piece. Okay? So we'll keep things simple. We'll put this bent wire in a constant magnetic field. Okay? All right, so we'll break it up into little pieces. Here's this little piece. The force on this little piece is, there's that force. I is the current. ds is the length of that little piece, cross B. Okay. So can anybody tell me the direction of this force? What will be the direction of the force be on this guy? Okay, so you take this screw and turn it in this direction, it'll come out of the plane of the paper. Okay, so df on this guy will be outside the plane of the paper. Okay. So if all this is in this, lying in this plane, the force on each little piece will be out of the plane of the paper, and then you can just add them up. All right, we're going to do that. So here's a wire. Okay. We've broken it up into little pieces, and we want the net force on this wire is just the sum of all those forces, and the sum of all those forces is an integral. So the net force is the sum of all the little forces, and the summation is just an integral. Okay. All right, so now what we're going to do is we are going to keep this magnetic field constant, so the field comes out of the integral, and so the integral just is a sum of these guys, little pieces, the sum of those little arrows. The sum of those little arrows is this vector going from the starting point of the wire to the end point of the wire. Okay, so it's I L L prime, okay, cross B. All right, so the force on this wire is given by that. So let me ask you this. What is the force on this wire? Hmm? No, the current. This wire has the same endpoints as this wire, so the force will be the same. Okay? So what is L prime? L prime is a vector pointing from the start of the wire to the end of the wire. What is the force on this wire? 0. L prime is 0. Okay, so the net force on a closed loop in a uniform field is 0. Okay, so the net force is 0, meaning the loop won't move in any direction. Okay, the center of mass of the loop will be stationary. But we'll come to a very important thing now. Okay, so now let's talk about that. Okay, in a uniform field, if you loop a wire carrying a current, the net force on it is 0. Okay, but let's see what happens. Okay, so here is a uniform field. We'll take a loop of wire like this. Okay, and now let's calculate the force. Remember, the force on a piece of wire is L cross B. Okay. All right. If the current is parallel, anti-parallel, or parallel to the magnetic field, L cross B would be 0. So the force on these guys would be 0. What's the force on this guy? Okay, so there's L is L is pointing in this direction. That's the direction of L here, and this is the direction of L there. Okay. So for this guy, the magnetic field is pointing like that, and if you turn a screw from like this, if you turn a screw like that, if you turn that screw like that, the screw will come out. So the force on this guy will be in this direction, coming out of the plane. For this guy, L cross B, this is B, the force will be into the sheet, into the plane of the paper. Okay? And it turns out that force on 2 and force on 4, the magnitudes are the same. So the net force on this is 0, except that what will this do? Now let me clean this up. So, okay, force F2 is like that, and force F4 is like this. They're equal magnitude. They're equal to I times A times B. They're equal magnitude. So the net force is 0. But what will these forces do? I'm sorry? They'll make the loop spin. So if you have a loop of wire in the presence of a magnetic field, you pass a current through the wire, what did you do? It's suddenly spinning. There's the electric motor. That's how the electric motor works. What did you end up doing? You ended up converting electrical energy to mechanical energy. Did you guys understand that? Do you know who does most of the work in the world? What? 90% of the work is done by electric motors. So this is at the heart of it. Did you guys understand that? All right, so the torque, what is it that makes things spin? Torques make things spin. So let's calculate the torque about this axis. It's force times the moment arm. Force times the moment arm. This is making it rotate counterclockwise, looking at it from there. This is also making it rotate counterclockwise. The torque is F2 times the moment arm, which is B by 2. B is that length. F4 times B by 2. And this, so this is IAB, and If you add the two, you get IAB times B. I is the current. A is the area of the loop. So the torque on that loop is the current in the loop times the area of the loop times the magnetic field. Okay. So it's I times the area of the loop times the magnetic field. All right, so you want to apply a greater torque, what do? You increase the area of the loop, or you increase the current, or you increase the strength of the magnetic field. Okay? Okay, so here you've learned a very important thing. Okay, what have you learned? If in the presence of a magnetic field, if you pass a current through a loop, you can make the loop of wire spin. Okay? Again, that's the basis of the electric motor. Okay? All right. Now, let's. So, which way will it spin? It spins like that. Okay. I'll show you an easy way to remember this in a second. Okay. So, the torque. So, right now here is the current carrying loop. If it is at an angle to the magnetic field, okay, so now we'll associate an area vector. And area vector will be, you point your fingers, use your right hand, point your fingers in the direction of the current, your thumb points in the direction of the area vector. Okay, so you use your right hand, point your fingers in the direction of the current, and your thumb points in the direction of the area vector. Okay, so if the current is flowing like that, and that's the area vector, and the magnetic field is pointing in this direction, so the loop turns towards the magnetic field. Okay, what the torque does is it makes the loop turn towards the magnetic field. Okay, that's the direction in which it will turn. Okay, so the torque is given by I times the area of the loop. Okay, area cross B. Okay. All right. So a current carrying. Okay. Now before we do that, let me ask you something. Okay, so let's say you might know this. Here's the magnetic field, and let's say you have a magnet like this, north pole, south pole. If you place a magnet like that in a magnetic field, what happens? Very good. The north pole feels a force like that, the south pole feels a force like this. So what it does is it lines up like that. The magnet lines up with the magnetic field. Okay, and that's what the compass needle was doing. See all the compass needles? If you initially pointed them like that, they would line up like this. Okay, so if you had a compass needle pointing like this, north south, the magnetic field will line it up with the field. Right? Okay. So this guy, this current carrying loop, is acting like a magnet pointing in that direction along the area vector. And all that the magnetic field is doing is lining up that magnet with the magnetic field. Okay, so a current carrying loop is called an electromagnet, and here is the strength of the magnet. So a current carrying loop is a magnet pointing along the direction of your thumb. Your fingers point in the direction of the current. Mu is the magnetic moment, which is telling you how strong the magnet is. Okay, and mu is N. N is the number of loops of the wire, times I, the current flowing in, times the area vector. Okay, so the strength of the magnet is N, the number of loops, times the current, times the area. So you can make a very strong electromagnet by just increasing the number of loops. Okay, so you want a strong magnet, you have greater number of N, or pass a large current, or have a large area. Okay. All right. So again, now you've learned a very important thing. Okay, let's make sure we remember this. So let's say you have a magnetic field like that, and you have a loop of wire carrying a current like this. Okay. If that's the current status of it, okay, again, point your fingers in the direction of the current, and the magnetic moment points out. Okay, and what is this magnetic field going to do? It's going to turn it like that. Okay, it'll make it spin. Okay, well, in this case, so what does it do? It makes it line up like this. Okay, so the loop will be perpendicular to it, and then because it has velocity, it will overshoot. And then what you do is in an AC motor, and then you switch the direction of the current. As soon as it gets there, you switch the direction of the current, so it'll keep spinning like that. Okay. All right. Again, a current carrying loop is a magnet, and the strength of the magnet, known as the magnetic moment, is given by N times I times A. Okay, and the torque on the magnet is torque on the moment is mu cross B. Okay. All right, so here it's showing you, so what this is indicating is there's a loop of wire, and you're looking at it crosswise, edge on this leg the current is coming out, and this leg the current is going in. Okay, so point your fingers along there. Your thumb is pointing in the direction of the magnetic field. There's no torque on this guy. Okay, and there's maximum torque on this guy. Here mu is pointing like that. Mu is pointing like this. Mu is pointing like that. Okay, and the maximum torque is on this guy. Okay. All right, so let's say you had a magnetic field in this direction, and you had a loop of wire carrying a current like this. Okay, what will happen? The magnetic field will apply a torque that'll want to turn it this way. Okay, so it'll want to turn the magnet so that it lines up like this. Okay, so initially it was at rest, and as it's turning, it's gaining kinetic energy. So just like when you drop a ball from a height, it had potential energy initially, and that potential energy gets converted to kinetic energy when it falls. So just like that, this has potential energy in the magnetic field, and when it gets turned like that, that energy gets converted to kinetic energy. Okay, so the potential energy is given by this mu dot B. Okay, right now the potential energy is 0 if mu and B are perpendicular, and potential energy will be maximum when it's lined up in the opposite direction. Okay, and potential energy is minimum when it's lined up with the magnetic field. All right, so we learn all this. Why are we learning all this? Let's talk about an application. This is very neat. Okay, so let's say you have a satellite up there, 500 miles up, and for some reason you want to turn it in this direction. Okay, what you could do is you could have a wire inside the there. And if you pass a current in this wire, that will be mu. Okay. And if you have if the Earth's magnetic field is pointing in this direction, you pass a current, this loop will want to turn in this direction. And see, the angular momentum of this thing was 0, so the satellite turns in that direction. Once you have turned the satellite all you want, you shut off the current there. This stops turning, the satellite will stop turning. Did you guys understand that? So you want to turn a satellite, you press a key on your computer when the satellite is turned enough. Let's go. All right, so these are called torquers. Many satellites use coils called torquers to adjust their orientation. Torquers interact with the Earth's magnetic field to to turn the satellite. Okay, now this technique can be used to turn satellites when they're close to the surface of the Earth. But if you have a satellite, a geostationary satellite that's 36,000 kilometers above the Earth, then the field gets too weak and you can't use that. How else would you turn a satellite if you can't use this? I'm sorry? Thrusters. What's the problem with thrusters? What?
Requires a source of fuel.
You need fuel. If the satellite is going to be there 20 years, you don't know how much thruster you'll need. And launching weight is expensive. So for a current, you can charge batteries using solar cells, and you'll always get the cells charged. Okay. So these are very useful. All right, now we'll do some fun stuff. Okay. So what are these crosses telling you? Very good. The magnetic field is into the sheet of the paper. Okay, now what we'll do is we'll go to a store and buy. So imagine in this room, the magnetic field is in that direction. We'll go to a store, buy a proton, and throw it like that. Okay. The force on this proton will be V cross B is in this direction. Okay. See, if you turn a screw in that way, the screw would move this way, so that's the direction of the force. So this proton gets deflected like that. Let's say when it's here, there's the velocity, V cross B is a force in this direction. It gets deflected like this. When it's here, it's V is like that, V cross B, the force is in that direction. So you take a charged particle in a magnetic field and throw it perpendicular to the field. It goes in circles around the field lines. So in this room, if the field is in this direction, you take and throw a proton like that. The proton is moving in circles now around the field lines. You guys understand that? What good is this? Well, you can do the following. Let's say you had a bunch of proton gas at 1 billion degree Kelvin. What would happen if this gas hit the wall? It would vaporize the walls instantly. But what if you want to contain this gas? All you do is just create a strong magnetic field, and the protons will just go in circles around the magnetic field lines, never hitting the walls.
Is that kind of like how our atmosphere is?
What's that? Very good. Let's see, now you know. So why are we interested in that? Okay, this proton is going like this, and so there are other field lines. This proton is going like that. You can have other protons going like this, and now this proton can collide with this proton. if they're moving super fast, they can collide with each other. Why do you want protons to collide? Okay, so let's say we get 4 protons colliding. This is what happens at the center of stars. They collide and they become a helium nucleus. So in this process, I'm leaving out some details. 2 of the protons got converted to 2 neutrons and so on. When will they form a bound nucleus? Why aren't these protons flying apart?
They're within that.
There's a strong force. They need to come within 10 to the minus 15 meters, and the strong force will take over. Okay. Well, when they combine, the mass of the helium nucleus is less than the mass of 4 protons. And that missing mass got converted to energy. So here's an infinite clean source of energy. This is how all stars make energy, and this is a fusion reaction which we would like to do here on Earth. Okay. And so you guys so here's a plasma which is probably at hundreds of millions of degrees. Okay. And so what is happening is, so there's the magnetic field lines, concentric circles, and protons are going around those magnetic field lines. They're trapped in the magnetic field lines. Okay? And if they have any velocity parallel to the axis of the tokamak, they'll go in circles. Okay? So what the protons are doing is they're going around in field lines and going around there. And so now you have, so here's hundreds of millions of degree plasma that's never hitting the walls, so it's not vaporizing the walls. And when the protons in there collide, they'll fuse and produce energy. Okay? Did you guys understand that? So this is replacing nuclear reactors. Okay. What is the problem with nuclear reactors? I'm sorry? Yep. Nuclear waste, that's radioactive for 25,000 to maybe 100,000 years. But it's not a big problem. But anyway. All right. I know we are saying a lot. Okay, so you see that field lines will trap charged particles. They're going in circles around the trapped particles. What this is the angular frequency. Okay. How many times a second they're going around. Okay, F is how many times a second they're going around. So 2 pi times that is the angular frequency. Is Q the charge times the magnetic field times divided by the mass. So bigger the mass, bigger the circle they're going in. Okay, and so on. So this is called the cyclotron frequency. Okay. All right, so what I want you to remember is, if you have a magnetic field, you throw a charge perpendicular to the magnetic field, it'll go in circles around the field line. Okay. Now, if you throw it at an angle, there's a velocity perpendicular to the magnetic field, which will make it go in a circle. Parallel to the magnetic field, that velocity doesn't get affected, so it'll go in helix in a helical path around the field lines. Okay, so if you throw it at an angle, it'll go in a helical path. All right, I'll tell you, you'll learn something cool now. Just be patient. So here's a stronger magnetic field, here's a weaker magnetic field. Okay, so a charged particle is going on a helical path. When it hits a stronger field, it feels a force in the opposite direction. So field configuration like this will be reflecting, so it won't hit that wall. The charged particle will go in a helical path, get reflected from there, and then go back and forth. So these are called magnetic bottles. So here's a magnetic bottle that will hold a plasma that's hundreds of millions of degrees Kelvin without melting. You guys see that? Yeah. All right, why do we talk about this? Okay, so from the sun, the sun is ejecting protons and electrons. Hot protons and electrons will escape from the sun. This is called the solar wind. And when it hits the Earth's magnetic field, they get trapped. These charged particles get trapped. And these charged particles then will go in that direction, and then the strong field will reflect them. This strong field will reflect them, and they'll go back and forth. So imagine the Earth, and imagine donut-shaped regions of charged particles around the Earth. Those are the Van Allen belts. And so what's happening is, so this donut-shaped charged particles, these particles are going back and forth, bouncing back and forth. Okay, they'll cover 20,000 miles in just a few seconds. They're very fast-moving particles. Now, but here's the fun part. Okay, so when they come close, if they come within 50 miles of the Earth's surface, those charged particles will start hitting the atmospheric molecules, and they'll excite them. And when the excited atmospheric molecules go back to the ground state, they emit light. What's that? Those are the auroras. Do you guys understand that? Okay, so those are the auroras. Okay, so here are some auroras. Okay, so this tells you what the colors are. Auroras result from emissions of photons in the Earth's upper atmospheres, about 50 miles from the ionized nitrogen atoms regaining an electron, and oxygen and nitrogen atoms returning from an excited state to ground state. Because these colors tell you oxygen emissions are green, so these are excited oxygen atoms. Okay, again, what is happening? These charged particles trapped that are running into the colliding with the atmospheric molecules and exciting them. Okay. So that's oxygen. Nitrogen emissions are red, blue and red. So that's nitrogen and nitrogen emissions. So these are called aurora borealis. These are called aurora australis. So if you go to Antarctica and see the polar lights, auroras, those are called aurora borealis in the southern hemisphere. Look at this. Auroras on Jupiter. This is Earth's auroras seen from the space station. Saturn's auroras. Okay, so this is important because soon as you see auroras, that means that planet has a magnetic field. Okay, you cannot have auroras without magnetic fields. And if you have a magnetic field, that means that you have a liquid metal core, because magnetic fields are created by currents. So the Earth's magnetic field, here is the North Pole, here is the South Pole. Okay. The magnetic field is that. Okay. The Earth's magnetic field is like this. Okay. So it's really created by a current flowing in that direction. Okay. So there is this is the current flowing in the liquid outer core of the Earth. Okay. So that's why this is important. Soon as you see an aurora in a different planet, you know that it has a liquid metal core. Now here's a neat thing about the Earth's magnetic field. So this current is steady, and on the average it's steady for 250,000 years, and then in a blink of an eye it'll reverse directions. We don't know why. Okay? And a blink of an eye is 2 to 3,000 years. So apparently we are in the middle of a flip. So our magnet is flipping in the middle of a flip. So if you come back, let's say 3,000 years from now, all your compasses will be pointing south. Okay? So come back 3,000 years from now, and then you can return your compasses and get all your money back. All right. What this is a velocity selector. Okay, what that means is the following. So the magnetic field is into the sheet of the paper. So this is a capacitor, two metal plates. You charge the capacitor and produce an electric field like that. And in addition, there's a magnetic field perpendicular to this. You take whatever it is that you're studying, heat it up, and also it gets ionized. So here are charged particles coming out. Okay? And they're coming out, there's a bunch of charged particles coming out with all velocities. Okay? And it turns out that, so it's a charged particle, the electric field, so let's say they're all positively charged, the electric field will deflect them downwards. Okay? And if it's moving in this direction, the magnetic field exerts a force in the upward direction. Look at this. The electric force depends on the charge. The magnetic force depends on the velocity. So only for a given velocity, this force will match that force. So for a given velocity, that particle will go undeflected. If it's moving too fast, it'll hit this plate. If it's moving too slow, it'll hit this plate. Did you guys understand that? So here's a device. So here you're spitting out charged particles with all kinds of velocity, and this device is selecting only one velocity. That's why it's called a velocity selector. It spits out particles of a single velocity. And you can adjust that based on the electric and magnetic field strength. All right, well, why do we need this? That periodic table has given you the masses of all those atoms. Okay, so for instance, the mass of the hydrogen atom is 1 atomic unit, right? And this is equal to 1 times 1.67 into 10 to the minus 27 kgs. How the hell did they weigh that? You guys see that? That's given to 2, 3, 4, 5 decimal places. Do you guys understand that? 10 to the minus 27 kgs, they've given it to 5 decimal places. How do they weigh that? Here's how they weighed it. Okay, so you want to weigh hydrogen, you ionize hydrogen, shoot it through there, and through the velocity selector. So you know a hydrogen ion with a precise velocity. And then shoot it in a magnetic field, and it'll go in a circle. And the radius of the circle is related to the mass of the atom. So the mass of the ion divided by the charge, so generally you give it one unit of charge, is related to the radius of the path. This is a mass spectrometer. This is how you weigh atoms. Our chemistry lab has them. Have you guys used it? The mass spectrometer? All right, so anyway, so here's the velocity selector in that. Okay. Cyclotron. Okay, I'll mention this Hall effect. Most of the times you won't deal with it, but okay. So let's say you take a flat wire, okay? And what you'll do is we'll pass a current through it in this direction. And in addition, what we'll do is we'll apply a magnetic field perpendicular to the conductor. Okay, so if you pass a current through there, if the charge carrier is electrons, so when the current is moving that way, it's really electrons moving in this direction. That's what happens in metals. But in semiconductors, you have charges that are holes, that can be purely holes, and so on. Okay, if it's electrons, what will happen is the electrons will, okay, so the magnetic field, if a positive charge was moving in this direction, positive charge would feel a force in this direction, but since they're electrons, they'll feel a force in this direction. They'll get deflected, so a bunch of electrons will collect here. This end will become positively charged, and eventually the force on the electrons will be that. So eventually the equilibrium condition will be, you're passing a current like this in the presence of this magnetic field, a bunch of electrons collect, and in a direction perpendicular to the electric field, you get a voltage develop, and that's called a Hall voltage. And this is useful, so the Hall voltage, which is the voltage perpendicular to the direction of the current, is equal to I, the current flowing, times the magnetic field, times this length, divided by N, the charge density, times the charge, divided by area. All right, this is easy to measure, this is easy to measure. So by measuring this voltage, you can measure the strength of the magnetic field, or you can measure charge density or the carrier type. Okay? So there's a lot of information you can get by measuring this voltage, and that's called the Hall voltage. And that's the voltage perpendicular to the direction of the current in the presence of a magnetic field. If this magnetic field was not there, if B was 0, the Hall voltage would be 0. Okay. Wow, that's a lot of information. You guys want to know about MRIs, or are you tired? All right. Before I do MRIs, I'll let you think about it. Let me show you how. Do you guys know how speakers work? What? So how do you get it to vibrate?
Inside there, you change the polarity
How do you change the polarity of the magnet?
through different charges going in.
So now you just learned about oh, there you go. Where are my tabs? Oh. How do I find my speaker tab? You guys saw that speaker? All right, I'll just draw it. All right, so yeah, you want to hear this. You have to go to the bathroom bad? Okay, go to the bathroom. I'll wait for you. Oh, we're recording this. All right. You explain it to him. Mhm. So here's a speaker. Here's a wire. And this is a magnet. This is a permanent magnet. Okay. If you pass a current in this wire in this direction, what happens? This becomes you point your fingers in the direction, it's thumb like that. This is acting like a magnet in this direction. Okay? So when the current is flowing in this direction, this guy will be attracted to that. And now, if you switch the direction of the current, if the current is flowing in the opposite direction, so this will be North Pole, this will be a South Pole, and this guy will be repelled. So, you see, by switching the direction of the current, you can make it attract to the permanent magnet or repel the permanent magnet. And so all you have to do is now attach a diaphragm to that. And by switching the direction of the current, by passing an AC current, you can make this guy vibrate up and down. And that's how a speaker works. How does a microphone work? There's a symmetry in everything. In a microphone, when you're talking like that, and you haven't learned this law, but we'll learn it later, when you are talking, you're making the diaphragm vibrate. And when a piece of wire, you'll learn this in a little bit, when a piece of wire, this is not carrying a current, when it moves in the presence of a magnetic field, a current is induced. So you have converted mechanical motion into electrical signal. Okay. All right, that's how the speaker works. All right, so this is an electric motor. Okay. Here's a magnetic field. And, okay, again, this should be in the next chapter. Okay. You take a wire and turn it in the magnetic field. And as the flux changes, that induces a current. Oh, no, this is motor, electric motor. Okay, so this belongs here. You pass a current, and you saw that it experiences a torque which turns. So electrical energy is converted to mechanical energy. Okay. All right. It's been a long lecture. Did you want to hear about MRIs? Or we'll stop? What's that? Anybody want to hear about MRIs? We're good? You want to hear about MRIs? Just a little bit. Okay, I'll give you a 30-second lesson on MRIs. All right, so here's the neat part about it. Okay, so let's say we want to take the head, MRI for a head. So you're taking a picture of that point inside the head. How the heck do you take a picture of that point inside your head? In the middle of your head. Do you guys understand what I'm saying? All right, so let's see how to take a picture of that. Okay. I'm going to keep it very simple. All right, so here's a magnetic field. Here's a little magnet. Okay. And now when I draw a magnet, the arrow is the North Pole and the tail is the South Pole. Okay. So if you put a magnet in a magnetic field, what will happen? It will want to line up with the magnetic field. Okay. So And what does it line up? This is a low energy state. And when it's in the opposite direction, that's a high energy state. Okay. Now, classically, it can be in any orientation, but quantum mechanically depends on the spin. Okay, so if it's a spin half particle, it can either be in that direction or in that direction. And again, I'm very simplifying very much. Okay, so now the magnet we'll take is a proton. A proton is spinning and it's acting like a magnet. So the hydrogen nucleus is your magnet. The hydrogen nucleus is a proton. Does your body have hydrogen in it?
Yes.
Where is the hydrogen?
I assume there's some hydrogen.
You are 80% water. Every water molecule has 2 hydrogen atoms.
He got you.
So you're full of hydrogen. You're full of hydrogen. All right. So we're going to take a picture of the hydrogen. Okay? All right. So let's see how we do this. Okay? So you saw that when the proton is lined up with the magnetic field, that's a low energy state. This is a high energy state. Okay? Now we'll draw it like so. So this is the high energy state, this is the low energy state. Okay? How do you jump from a low energy state to a high energy state? You shoot a photon of the right energy. Okay? You guys understanding this? I'm giving it at a very fundamental level. So you shoot a photon from here to there, then you can go from this low energy state to high energy state. So what you're doing is when you shoot a photon, this proton spin flips, that's all. It went from low energy state to high energy state. Okay, this photon energy matched this energy. Now the energy difference is proportional to the magnetic field. The energy difference, let's say, is some constant times the magnetic field. Okay? There's the punchline. Did you guys understand that? All right. Now, the trick is the following. So let's say you want to take a picture of that particular spot. There's hydrogen everywhere, but you want to take a picture of only that spot. What you do is, at that particular spot, you make the magnetic field what you want it to be. Everywhere else, the magnetic field is different. So the photon that you're shooting only matches the energy level difference at that spot. Only hydrogens at that spot are absorbing the photons. Okay? They absorb the photons and, within a millionth of a second, they'll emit it back. Okay? So you take a coil that's shooting these photons. Those hydrogen molecules absorb the photons, and within a millionth of a second, they'll emit it back, and this coil would detect them. So you got a picture of that spot. Are you happy? No. Well, now you take a picture of the next spot. So you change the magnetic field so that the next spot has the right magnetic field. Okay? And then you take a picture of the next spot. And then you take a picture of the next spot. And then you have computers to put all those spots together for your MRI image. Okay? So what this is, okay, so here's an MRI machine. In this slot, there is a strong uniform magnetic field. And then you have gradient fields that increase in that direction, and increase in this plane. So you can change the field according to what you want at precise spots. Okay? So you're changing the magnetic field such that the energy level difference matches the energy of the photons that you're shooting. Okay? So you're taking pictures of one spot at a time. Okay? So that's a 30-second description of MRI machines. Again, there are great devices. They use very strong magnetic fields. You see, here's a magnetic field of 2 to 3 Tesla. That'll make a gurney fly. So if you're not careful, it can be a dangerous thing. All right.